Okay, so good news, everyone. It's time to start. So how's everyone today? Super. So some of your questions, your exam questions are graded, and they'll be posted probably today or tomorrow. So as the questions get graded individually, I'll post them. So don't panic if you see just 4 grades put into the grade book, and they're not, and 4 being less than 6. Please don't worry too much about that. Okay, until they're all in. Good. So any questions before we get to it? Okay, so then today's what? The 21st. So last time we were talking about inverse functions. Okay, so the way we framed it is that composition is like anything else, like any other operations. So addition is an operation that you can do on numbers and also on functions. So, but numbers are simpler, so let's stick to numbers for a moment. What is the additive identity? 0. Why is 0 called the additive identity?
Because you can add it to x and x does not change.
Right. The procedure of adding 0 to something does nothing, right? So x plus 0 is x for all x's. Okay. What is the additive inverse of 7? Negative 7. That's a fact. But now, why is negative 7 the additive inverse of 7?
7 minus 7 is 0.
Right, because when you add these numbers, 7 plus negative 7, you get 0. Okay, which is the additive identity. Okay, now, which numbers have an additive inverse? All of them. All of them do. Okay, and then what is the formula for computing additive inverse? What's the formula? So that establishes that 0 is the identity. It's an axiom. It doesn't establish anything. It's given to be true. So why is it? No. I already asked that question. What is the formula for additive inverse? It's always negate. So what is the additive inverse of 7? Negative 7. What is the additive inverse of negative 10? 10. Negative 10. Right. So the formula is always negation. Okay, so addition is nice. The identity is easy to understand. All numbers have an additive inverse. The formula is negation to compute additive inverse. So another operation is multiplication. What is the multiplicative identity? 1. Okay. Why is 1 the multiplicative identity? Right. Multiplying by 1 is the same as doing nothing. Okay. Suppose I give you, no, let's do that. Suppose I give you 5. What is the multiplicative inverse of 5? 1 over 5. Why is it the case that 1/5 is the multiplicative inverse of 5? Because the product of these numbers is 1, which is the multiplicative identity. So that being the case, then, what is the formula? Supposing that I give you an x which does have a multiplicative inverse, what is the formula for the multiplicative inverse of x? Reciprocal. 1 over x. Now, does every number have a multiplicative inverse? Every non-zero number. So if I give you a number which isn't 0, then it is in principle possible to find its multiplicative inverse. Now, why does 0 not have a multiplicative inverse? It's not because 1 over 0 is undefined. It is not defined. I agree with that.
The product of something times 0 would never be 1.
That's right. To say the request to find the multiplicative inverse of 0 is to say, I want you to produce for me an x so that 0 times x is 1. There are no such x's. That's why it's not multiplicatively invertible. That's the reason. Okay? So we talked about, so in that context, then we said, now composition is an operation just like this. It has an identity. So what is the identity of composition? ID. ID function. Because we showed that if you do f circ ID, f composed with ID, evaluate at x, that's the same as f. And if you do ID circ f evaluate at x, f composed with ID, that's the same as just f. So composing f with ID on either side doesn't change f at all. That's why it's the identity of composition. Taking the point of view that functions are like machines, the ID function is like, and taking that composition is like putting machines in order like an assembly line, the ID function is like a stretch of conveyor belt. The X just moves along to the next bit. So, you know, if we had an assembly line that was putting socks and shoes on a doll, it doesn't really matter the machine that puts on the left shoe and the machine that puts on the right shoe. It doesn't matter if they're 1 meter apart or 100 meters apart. It doesn't make any difference. Okay? Now, that addresses what the identity is. It's the identity function of composition is ID. How do you tell when a function is in fact invertible? So just like, what numbers have an additive inverse?
1 to 1.
Right. So functions which are 1 to 1, they're the invertible kind. So just like what numbers have an additive inverse? All numbers have an additive inverse. What numbers have a multiplicative inverse? All non-zero numbers have a multiplicative inverse. What functions have a compositional inverse? 1-to-1 functions have a compositional inverse. That's the ones that have a compositional inverse. So 1-to-1 with arrow diagrams, that means that in the range, there's only one way to reach something in the range. No two things, no object in the range has two arrows pointing to it. That's what 1-to-1 means when you're doing arrow diagrams. If I was to plot a function for you, how do you tell if a function is 1-to-1? The horizontal line test. Horizontal line test. So if I was to give you a drawing, if I was to give you a bunch of drawings of functions and I was to say which ones are invertible, that's equivalent to me asking, perform the horizontal line test on each one of these functions. And I think we did that last time. Okay. So now what we need to address today is, okay, we know what the identity of composition is. We know how to tell which functions have an inverse. Now we need to figure out how to actually compute the inverse. Just like the formula for additive inverse is negation, the formula for multiplicative inverse is reciprocal. What is the formula for function inverse? Yes, and it is transposition. Okay, so the following. So let's do an example. Picture. Okay, so suppose I give you this function. Yeah, that'll be fine. I'll put that right. What do I want to do? Yeah, okay, this one. I need one of those. Okay, so here's a function. Or here's a plot. Okay, so my first question to you is, so is this a function? Okay, so how do you confirm or deny that?
Passes the vertical line test.
Vertical line test. So yes, it passes the vertical line test. Okay. So is it invertible? Okay, so how do you confirm or deny that? Horizontal line test. Okay, so now it is, okay, you've told me it's a function, you told me in fact it's an invertible function, so now I want you to draw what its inverse looks like. Okay, so this is the way to address that question. So what if I was, the red function, what if I was to give it input 4? What output would it produce? 2. When I give it input 4, it produces output 2. Okay, so that point right there. So that means that for the inverse function, if I was to give the inverse function input 2, it should produce what? Output 4. That is to say that because this is the point 4, 2, what point must be in the inverse? 2, 4, the transposition of that. 4, 2 is in the input, 2, 4 is in the output. 4, 2 is in the function, 2, 4 is in the inverse function. Okay, so right here. So this point 4, 2 is in the original function. This point 2, 4 is in the inverse. Interesting. Okay, so how about, what are the coordinates of this point? 2, -1. 2, -1. So that's in the original. What's in the inverse? -1, 2. No. 2, no. This is 2, -1. Oh yeah, so -1, 2, sorry. Sorry, brain is just not cooperating. Okay, right here. Okay, so then we could do this with every single one of those points. So if the point AB is in the function, then what's in the inverse? BA. Transposing these. So now, this is going to be equivalent to the following. So now I'm going to draw the line y is x. And what I want you to observe is that we found that 4, 2 was in the original, and 2, 4 is in the inverse. And 2, -1 is in the original, and -1, 2 is in the inverse. So how are these related to each other? Reflections. They're reflections of each other. So we can do it generally by just taking the whole red and just flipping it over. So can anyone see a point that reflects to itself? How about that one? Right, that point doesn't move, and whatever that is doesn't move either. That doesn't happen to go through an integer coordinate, but it doesn't move either, right? So this one doesn't move, and this one doesn't move either. And then how about, where does this one go? So you could do the coordinates, but can you just see it with your eye where it's supposed to go? Yeah, right here. And now, connect the dots. Okay, now this is not an art class. Okay, so I'm not grading you on your ability to draw straight lines by freehand or something like that. But whatever you produce, if I was to give you such a question, it needs to look symmetric. Okay, more or less. Okay. Okay. If it doesn't look symmetric, then that's not going to work. Like for example, if I give you a picture, that looks like this, like say, like that, and I give you this line, and I say compute the inverse. Okay, if you draw something that looks like this, that's not going to work. Okay, because it's not symmetric, right? This won't work. Okay. Any question about this? So now, if I was to give you a whole array of such pictures, like a question with like 4 of these on there, and I've said, okay, here's 4 plots, compute the inverse. Then the very first order of business for each one is to check, well, does it have an inverse in the first place? So what if I was to give you, in your mind's eye, imagine that one of the plots I give you is a parabola, and I said compute its inverse. How should you respond to me? You should say that there is no inverse. Why is there no inverse for a parabola? Doesn't pass the horizontal line test. Doesn't pass the horizontal line test. So you should respond that no, in fact, there is no inverse. Okay? And then if I do give you one, like the red one, that is in fact invertible, then you say something like, okay, yes, it is a function. Yes, it is an invertible function. So here's the inverse. Okay? Any questions about that idea? So now, this is how you do it with pictures. Now the question is, what if I ask you to do it with formulas? Okay, what about that? So for example, if I give you that f is, say, 5x minus 2, I'll say something like this. Assuming f inverse exists, compute f inverse of x. So this clause here means that I don't want you to show me that in fact the inverse exists in the first place. Just it does. I'm telling you that it does, and I want you to compute it. Okay. So the reason, the practical reason for this is that for some functions it's a little complicated to show that an inverse function exists. And this part, if I was giving you a picture, I would be saying, don't bother doing the horizontal line test. That would be what this is saying. But I don't ever say that when I give you a picture, because human beings can do the horizontal line test with their eyes closed. Not really, but just about, right? So I always, so this just makes the question easier to deal with in the end. So the way this works is as follows. It's really just a recipe. So you start out with the function. So this is just saying, okay, let's consider that function. Then what I'll do is I'll replace that f of x with a y. Which means that now we're considering the graph of this function. If we were to draw the graph as a plot, how would we compute the inverse? So what is it that you do? Right, so if in the picture, when I gave you this, in the end, you could think of it in 2 ways. You could say, well, because 4, 2 is on the original, that means that 2, 4 is on the inverse. Or alternatively, if you were more of a picture person, you could just say, well, you're just asking me to draw this line and then flip it over. So that's what's being asked when you have a picture. Here, when we have formulas and not pictures, what we're going to do is we're going to swap x's and y's. Everywhere that you have an x, you're going to write y, and everywhere you have a y, you're going to write x. So what's the new equation?
X equals 5 minus 2.
Very good. Now, for those of you who have taken a course like this before in some other context, many students get to this position and they say, oh, I remember doing that. But they haven't connected it. What is it that we're doing here? What is this visually? So it is part of, it's all of those things, but what is this visually equivalent to? What did we just do? We reflected it. Exactly that. That's what this is. This is reflection across y is x. This is the formula. The formula manifestation of swapping x and of reflecting x across y as x. So now all that's required is now you solve for y. So supposing we wanted to solve for y, we do what? Add 2. And then divide by 5. So this stuff is just solve for y. Then the answer is that the inverse function is this thing, x plus 2 over 5. Okay, so now, sort of conceptually where we are, you can think like I gave you the following. So here's a number, 8. What's the multiplicative inverse of 8? 1 over 8, multiplicative. So 1 over 8 is the multiplicative inverse. So that's like what you did here. You said, I'm computing. Okay, the multiplicative inverse is 1 over 8. Then I say, well, why is 1 over 8 the multiplicative inverse of 8?
It's 1 over 8 times 8.
Because when you compute their product, when you multiply them, you get 1. So now I'm going to ask the analogous question. I'm going to say, okay, you did something, and you're claiming to me that this is the inverse function. Why is it that this function is the inverse function? Not multiply. Not transpose. Well, okay, transpose coordinates. So what? So there's additive inverse, multiplicative inverse, and what is this? Compositional inverse. So how are we going to show that this is in fact the inverse function? So if I gave you two numbers and I said, show me that these numbers are additive inverses, then what would you do? You'd add them. If I gave you two numbers and I said, show me these numbers are multiplicative inverses, then you would multiply them. And I've given you two functions and I'm asking you to show me that they're compositional inverses. You compose them. So now, if this was an exercise, this would be part 1. And part 2 would be, now I want you to verify this. And specifically what I want you to do is I want you to compose them in both orders. So f circ f inverse. Evaluate at x. Now, we're going to perform a computation, but what should happen when we do this? It should be ID. So what do you get? What do you get if you plug ID in? If you plug x into ID, you get x. So we're going to do this, and if we've done this right, then we should just get an x. That's what should happen. So we should say this and then blah 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 x. Okay. So how do we write this without composition? Without the composition operator? Okay, so I agree with that, but let's ignore the formulas for a minute. And I want f's and f inverses, but I would just want to write this without composition operator. So it's like this, right? So this one. So this the f inverse is inside because x goes to this one first and then the next one. Okay. So now f takes its argument and produces 5 argument and then subtract 2. So that would be 5 argument, and then subtract 2. So any question about getting here? Okay, then we can say what f inverse does. So that would be 5, and then x plus 2 over 5, and then minus 2. So look at this expression. It's a little complicated. It's saying, okay, I want you to take an x, then I want you to add 2, divide all that by 5. And after you've done that, I want you to multiply by 5 and then subtract 2.
That's going to be x.
So let's see. So what is a simplification I can do?
You can cancel the 5.
I can cancel the 5s. And now what?
Subtract 2.
Subtract 2. So is that good?
Yeah.
That's good. So what we're saying is that this function is the function that takes x and does
But
nothing. It just gives it right back to you. But look at all the noise it makes, right? It would be like a machine that you put the x in, right? You put the x in, and then you hear all this, you know, drill motors, and then a saw, and then you hear all this stuff, and then the x comes out and it's, nothing happened.
X will be given to you.
Yeah. So now, because composition is not commutative, that means that we must do what?
Do the inverse.
We need to check it in the other order. Okay. So composition is not commutative because, for example, okay, if we had a doll factory and we were looking at the part of the assembly line where you're dressing the dolls, okay, it doesn't matter what order the left shoe and right shoe putter oner machines are, right? It doesn't matter for the final product. But if this doll was fancy and had socks, would it matter what order the left sock machine and the left shoe machine are in? Yeah, it would matter, right? Because if someone was playing a joke and put them in the order shoe first and then sock, it wouldn't look right. So it matters. Okay, so then f inverse circ f, evaluate at x. Okay, so how do I write this without the composition operator? Very good. Okay, so then f inverse does this. It takes its argument and produces argument plus 2 and divides all that by 5. So this would be argument plus 2, divide all that by 5. Okay, then what f does is it's 5x minus 2, so that would be 5x minus 2, and then we'll add 2, and then we'll divide by 5. So the 2's cancel. The 5's cancel. And there we have it. Okay, so we verified it. In this order, it's the identity function. In that order, it's the identity function. So we have, in fact, found the inverse function. This is just like me saying, okay, you know, in second grade or whatever, what's the multiplicative inverse of 2/3? Okay, it's 3/2. Okay, and why is it 3/2? Okay, then you multiply them and you say, oh, I got 1. It's just like that. Yes?
Anytime you ask us to verify, do you want us to put it both ways?
It must be done in both ways. Yes. And the reason is because composition doesn't commute. And I'll specifically check that because I'll give you functions where one of them works and the other doesn't. But once you find that one of them doesn't, then you can stop. So like, for example, if you say, well, here's 2 functions and I compose them in this order and I don't get x, no need to proceed any further. Any questions about this? Okay, so let's do another. So same question, different function. So if I give you f of x is 8x cubed plus 5, please compute the inverse function and then verify that you have in fact computed the inverse function. Assuming, and at this exercise you can assume that the inverse function does exist. No, it does. No, I said that it does, but I promise you it does. But I'm not asking you to verify if it does exist. But it does. Okay, so in the interest of time, really this is, like I said, just a recipe. First you write down the function. So this is the function that we want to invert. Then what?
First you change the f of x to y.
Yeah, we make this a y, which means that we're considering the graph. Now we're going to transpose the graph. And then if we were to make a picture of the graph, which is called a plot, visually what happens when you transpose the graph? You reflect it across y as x. So here comes the reflection step. And now we solve for y again. Right, subtract 5. Divide by 8. And cube root both sides. And so as a result, we've established that our presumed inverse is that thing. Okay, so any question about getting to here? Okay, so now what? Very good. So now we're going to verify. So f circ f inverse. Evaluate at x. How is this written without composition? Very good. So f inverse, because it's the one closer to x, it's still the one closer to x when you do this, right? This one's closer to x, that one's closer to x. Okay, so then now f takes its argument, cubes it, multiply by 8, add 5. So and then that's what f inverse is, f inverse of x. And I'd like to kind of point out just how crazy this looks presently, right? What is this supposed to be in the end?
X.
X, right? So what I'm saying is, okay, I want you to take that x, I want you to subtract 5, divide by 8, compute the cube root of all of that, then I want you to cube it, multiply by 8, and then add 5. Okay, that's what I want you to do, apparently. So then what's the first thing we can simplify? Okay. You can cancel the 8s. Cancel the 5s. So altogether, this is really a fancy way to say, I want you to take that x and do a whole lot of nothing. Just give me that x right back, please. Okay? So this is kind of like for any of you who've worked at Starbucks or have friends at Starbucks. All of them, if you've worked at Starbucks or have a friend that works at Starbucks, then they can tell you there's a standard Starbucks joke where someone comes in and orders something like, you know, I want to, and they go on a long list like, I want a mocha latte, blah, blah, minus the one shot and then plus the cream and then all this, and it turns out to be a cup of water, right? Ridiculous, right? It's just like that. Okay. Okay. So what's next? Right, same thing, other order. I had to remember that joke. I can't. I don't know enough about Starbucks to be able to do it. Okay, so then how do I write this without composition? Very good. So the f is closer to x. So when you write it without the composition operator, it will still be closer to x. Like so. And then f inverse does this. So it takes argument and makes argument minus 5, all that over 8, and then all that cube root. So that would be like that. And then f, substituting in what f does, and there we go with the complicated looking thing. So the 5s cancel. The 8s cancel. The cube and the cube root cancel. And we get x. Okay. So any question about this exercise? So now I'm going to ask the question a slightly different way. So supposing I gave you two numbers, 7/5 and 5/7, and I said, are these multiplicative inverses? Okay, so then, but I want you to, if yes, then show me why. So what would you do?
Multiply them together and get 1.
Multiply them together and show me that you get 1, which is the multiplicative identity. So now I'm going to ask you just that question, except I'm going to give you functions. I'm going to say, here's a function and here's another. Determine whether or not they are compositional inverses. How will you confirm or deny that?
If they're compositional inverses, you use the f inverse.
Right. You compose them and see if you get the identity. Okay. So here we go. So R, F, and G, compositional inverses. So f of x is x squared plus 1, and g of x is square root x minus 1. So what are we going to do? Okay. So f circ g, evaluate at x. What should I, supposing they are inverses, what should I get if I do that? I should get x. Okay. Well, that would be writing it without the composition operator. That'd be f of g of x. And then that would be g of x square that, add 1. And that would be square root x minus 1, square that, add 1. So now what? Okay. Okay. So, are they inverses?
So far,
So far, okay. Good, I like that. So why so far?
we haven't done yet the g.
We have to test the other order. Okay. Okay, so that would be square root f of x minus 1, all that under the radical, and then that would be that. So now before I get any further, I want to ask a different question. Are 0 and 9 multiplicative inverses? No, they're not. Okay. So what are we going to do here? Okay. And now I'm going to ask again, why are 0 and 9 not multiplicative inverses?
0 times 9 is 0.
Even there's even a reason even before that.
It's not the reciprocal.
It's even before that. There's a reason even before that.
0 doesn't have a multiplicative inverse.
0 doesn't have a multiplicative inverse.
Yeah.
So it surely isn't 9, right? Because it doesn't exist at all. So what's the next step? Oh, but no. What is the square root of x squared? Is it x? It's the absolute value of x. It's not x. It's not x. So, what's the conclusion about f and g? Are they inverses? This is not x. And therefore, f and g are not inverses. Now, I claim that you could have gotten to this right here immediately without doing any of this work whatsoever. None of this work was necessary. Are 0 and 9 multiplicative inverses? No. Why not? 0 doesn't have a multiplicative inverse. So it's not 9. This is a quadratic. In your mind's eye, what is the name of the shape of the plot of a quadratic?
A parabola.
Parabola. It's a parabola. And imagine a parabola in your mind's eye. Is a parabola invertible? What is the visual test for invertibility? Horizontal line test. Does a parabola pass the horizontal line test?
No.
No. I did this to prove a point. Okay? That we went off on this wild goose chase looking for something that doesn't even exist. Are f and g inverses? No, because f is not invertible in the first place. Of course they're not inverses. Are 0 and 9 multiplicative inverses? No, of course not, because 0 doesn't have a multiplicative inverse. Okay, now, here's a different question. Suppose I give you p of x is x squared plus 1, and I give you q of x is square root x minus 1. Suppose I give you that. And at the present moment, it's the same exercise as before, presently. But suppose I add the additional qualification that for p, it must be the case that x is greater or equal to 0. Suppose that I say that's the domain of p. Now in your mind's eye, I want you to imagine a parabola. It's symmetric about its axis. Now take only the right side of that parabola. Does that pass the horizontal line test? It does. So p and q in this case are going to be inverses, because when you get to this step, then it'll be the square root of x squared, assuming that x is non-negative, and you won't need absolute value, and it will in fact be x. So visually, this question was equivalent, in a sense, to me asking, well, here's f. There's f. Does it have an inverse? No. In fact, that's not f, because f needs to be shifted up one. That's f. So does f have an inverse? No. But here I'm asking, adding this red qualification is saying that, okay, this is the function I'm talking about. Does this function have an inverse?
Yes.
It does. And you could compute its inverse visually by drawing this line and doing what? Reflecting it. That's supposed to be symmetric. This would be good enough, okay? That's what I'm talking about, art, okay? This is not art class. Okay, I understand what you mean if you do that. Okay, good. Any questions about this? Yes?
So just knowing that x is greater than 0 when you take the square root in your mind, you just know it doesn't have to be upside down? Or
No,
did you do
no.
it?
So if I was to give you this exercise, then I would expect you to do it by hand and compute it. This column would be exactly the same. So if you do P composed with Q, this P composed with that Q, then the computation would look exactly the same. But then you'd get to this position right here. You get to this position right here on the analogous place, and you'd say, okay, equal to the square root of x squared, which is equal to the absolute value of x. But because x is known to be greater than or equal to 0, what is the absolute value of x? Just x. So this is possible because we know that x is greater than or equal to 0. That's why. So here, what's the domain? Because I didn't give you a domain for f, what's its domain? All reals. Because the domain of this f is all reals, that means that you don't know if x is positive or negative. But here, I explicitly gave you a different domain, so you do know, in fact, x is not negative. Okay, have a nice weekend.